Let's go! Number 5. This shouldn't be possible. A single event happens in a sealed box, and the universe refuses to pick one outcome. Yet, that is exactly the crack Erwin Schrödinger wanted you to stare into. In 1935, Schrödinger was in Zurich, trading letters with Einstein-era giants, watching quantum theory win every prediction while breaking every intuition. He publishes a short argument in Naturwissenschaften and builds a thought experiment. A closed box, one radioactive atom, a Geiger counter, a vial of poison, and a living cat. Atom decay triggers the counter. The counter breaks the vial. The cat dies. No decay, no trigger, no poison. The cat lives. Whether the cat is alive or dead, according to the raw quantum rules, is not, we don't know yet. It is, both outcomes exist in the math until a measurement pins one down. The atom can be in a superposition of decayed and not decayed, and that uncertainty spreads outward, to the detector, to the mechanism, and to the cat's fate. If you trust the equations with no special exceptions, the box contains not one story, but multiple mutually exclusive stories at once. That's the weirdness, not the cat, the rule it breaks. In everyday reality, events settle even when nobody is looking. A coin lands. A door is either locked or not. But the quantum formalism seems to say the world can hover between versions until something counts as a measurement. Yet, what counts? That's a good question. The mainstream operational view says collapse happens at measurement. Decoherence theory, built later by people like H. Dieter Zeh in 1970 and refined by Wojciech Zurek in the 1980s and 90s, says the environment is a relentless witness. Stray photons, air molecules, thermal noise. They entangle with the system so fast that interference between branches becomes unobservable, making one outcome look classical. Then, some interpretations say collapse is not physical at all, just an update in knowledge. Others say collapse is real and dynamical, like GRW-style models proposed in the 1980s by Gherardi, Rimini, and Weber, where superpositions spontaneously localize with a tiny rate that becomes huge for big objects. But none of this fully settles it. Decoherence explains why the branches stop talking to each other, but it doesn't pick a single winner. Collapse models add new parameters and are still constrained by experiments, not confirmed. And the shut up and calculate approach works, yet leaves the deepest question untouched. When did reality become one thing? If theory is correct, then your daily certainty is not fundamental. It's a limit case, a thin crust over a deeper ocean where incompatible versions can exist without contradiction. So here's the question that drags us forward. If a box can contain multiple outcomes at once, then can two realities coexist at once? Number 4. This seems impossible. Imagine two people look at the same quantum system, and reality refuses to give them a single shared description. Instead, reality is tied to observer. One interpretation says that's not a bug. That's the point. In the mid-1990s, at the University of Pavia in Italy, Carlo Rovelli sharpens an idea that had been lurking in quantum arguments for decades and turns it into a clear stance now called relational quantum mechanics. It's not a new equation. It's a claim about what the equations mean. The visual is simple. Imagine a quantum system, call it a spin, and an observer, call it a detector. The detector interacts with the spin and records an outcome. Relative to that detector, the spin now has a definite value. But to a second observer who has not interacted with it yet, the combined spin plus detector can still be described as an entangled superposition. Same physical situation. Two descriptions, both valid in their own frame of interaction. Why that's weird is that it attacks a bedrock assumption that properties exist absolutely, like a label glued to an object. Relational quantum mechanics says properties are not absolute stickers. They are answers to specific interactions. The state is not a universal inventory of reality. It's a relationship. Imagine two people watching the same soccer match from different seats. One sees a perfect offside line. The other has a bad angle and swears the striker was onside. The event feels objective, but what each person can honestly say is constrained by their viewpoint and what signals reach them. Relational quantum mechanics makes a similar claim at the deepest level. Properties like spin-up aren't absolute stickers on an object. They're answers that exist only relative to a specific interaction. Who measured, how they measured, and what record was created. This is aligned with what quantum experiments already force you to accept about measurement context. Think of the Stern-Gerlach experiment, first demonstrated in 1922 by Otto Stern and Walter Gerlach, where silver atoms split into discrete beams in a magnetic field gradient. The spin value you get depends on the measurement axis. The value is not a thing in itself. It is a thing for this interaction. Another explanation people prefer is the more conservative one. The wave function is just a bookkeeping device for probabilities. Different observers have different information, so they assign different states. No mystery. Yet, in relational quantum mechanics, it's not only about information, it's about what exists. A third explanation comes from Everett-style thinking. All outcomes happen, so different observers just land in different branches. Relational talk becomes a description of branching, not a replacement for it. Why none of this fully settles it is that relational quantum mechanics is persuasive but hard to test as a unique claim. Many interpretations reproduce the same experimental predictions, and critics argue it risks making reality too dependent on perspective without clearly defining what an observer must be. A photodiode counts, a dust particle counts, a human mind counts. The theory tries to avoid privileging consciousness, but the boundary still feels slippery. If it's right, then the universe is not one giant camera recording one objective film. It's a network of interactions where different parts of reality become definite only relative to other parts. One version for you, another version for someone else, until you meet and compare. So, here's the philosophical question. If facts are always relative, then what is a quantum state really describing? The world or you? Number 3. This one is going to blow your mind. You make a free choice in the lab, and the universe already knew what you would choose. Yet, one class of theories says that's the only way out. The story begins in the shadow of Bell's theorem. In 1964, John Bell showed that no theory with local hidden variables could reproduce all the predictions of quantum mechanics. Decades later, experiments by Alan Aspect in the 1980s and later loophole-free tests like the Delft experiment in 2015 confirmed the violation of Bell inequalities again and again. Entangled particles separated by kilometers behaved as if their outcomes were coordinated beyond any local explanation. What happened is simple to state. Measurement settings are chosen, outcomes are recorded, the correlations are too strong. If you assume locality and genuine freedom of choice, classical realism collapses. Superdeterminism proposes a radical escape. It says the problem is not non-locality. The problem is the assumption that measurement choices are free. According to this view, the particles and the experimenters are not independent systems. The hidden variables that determine the particle outcomes are also correlated with the choices of which measurements will be performed. The universe never allowed a mismatch. Think of it like a rigged but perfectly consistent escape room. You feel free to choose which lever to pull or which door to open. Yet every lever you reach for and every door that catches your eye was already accounted for when the room was built. Not because someone is cheating in the moment, but because the layout and your reactions were always part of the same design. Superdeterminism says the universe works like that. The particle's behavior and your decision of how to test it were never independent to begin with. It breaks the intuition that you can freely decide how to probe nature. The knob you turn, the detector you choose, the random number generator you trust. All of it is already part of the same causal web as the particle you're measuring. You feel like you're choosing, but that choice is just another outcome of prior conditions. Most physicists assume some degree of statistical independence because without it, science itself seems to wobble. If every choice is pre-correlated with what it measures, then testing theories becomes deeply suspect. Bell himself called this escape conspiratorial, yet some propose it seriously. Gerard at Hooft has explored deterministic models where quantum behavior emerges from deeper, fully determined dynamics. Others argue that superdeterminism doesn't require malicious conspiracy, only global constraints set by initial conditions of the universe. The correlations could be lawful, not engineered. Many say superdeterminism explains everything and therefore explains nothing because it removes the ability to rule models out experimentally. It preserves a single reality, but at the cost of making freedom and independence illusions. Why none of this fully settles it is that superdeterminism is almost impossible to falsify. Any experiment designed to test it can be absorbed into the theory itself. And yet, it remains logically consistent with all known data. It fits the correlations. It avoids branching worlds. It avoids faster-than-light influence. If this is true, then reality never splits. There is only one version. But that version is locked in from the start, including every question you will ever ask about it. So here's the question that should make you uncomfortable. If your choices were always part of the universe's script, how would you ever know you were free to choose otherwise? Number 2. This one breaks time itself. An event might be fixed only when both the past and the future agree on it. Yet, one interpretation builds the whole quantum world out of a handshake across time. In the 1980s, at the University of Washington, John Cramer proposes what he calls the transactional interpretation, inspired by older time-symmetric ideas in physics like the Wheeler-Feynman absorber theory from the 1940s. It takes something already present in the math and dares you to treat it as real. The picture is cinematic. A source emits an offer wave forward in time. Potential absorbers respond with confirmation waves backward in time. Where an offer and a confirmation match, a transaction forms. Energy and momentum are transferred. The quantum event becomes real. But until the handshake completes, multiple possible transactions exist, competing. Picture scheduling a meeting across time zones. You send an invitation. Potential attendees respond with confirmations. Only when an invitation and a confirmation match do you get a real meeting locked in on the calendar. Transactional interpretation treats quantum events like that. An offer goes out, confirmations come back, and the actual event becomes definite only when the handshake completes. Until then, multiple potential deals are on the table. Why it's weird is that it breaks the forward-only story we tell ourselves. Cause, then effect. Transactional thinking says the final outcome is not selected by a one-way push from the past. It is selected by a consistent agreement between emitter and absorber across time. You can translate this into standard quantum mechanics without changing predictions. Many see it as an interpretation that gives a physical narrative to complex amplitudes and boundary conditions, not a new experimental claim. It can make sense of puzzles like interaction-free measurement and some delayed choice setups without saying the past is rewritten, only that the quantum event is defined by the whole experimental context. Another explanation people prefer is the block universe or time-symmetric formalism route. The equations already allow boundary conditions at both ends. The transactional story is a metaphor for that mathematical symmetry. Why it doesn't fully settle it is exactly that. Testability. It raises deep questions about what counts as an absorber in quantum field theory and how to generalize the handshake cleanly in relativistic settings. It's debated. It's not consensus. Still, if the universe really selects outcomes via a handshake across time, then reality doesn't happen one moment at a time. Multiple possible versions remain open until the entire loop of possibilities closes. So here's the question that points to the final step. If outcomes aren't chosen by collapse and aren't chosen by a single observer, and maybe aren't even chosen purely in the present, what if the universe never chooses at all? Number 1, and the final one that will make you reimagine reality. Every quantum measurement has one result. Yet, one interpretation says that certainty is an illusion created by your position inside the branching. In 1957, a young physicist named Hugh Everett III, working at Princeton under John Wheeler, proposes a radical move. Remove collapse. Keep the Schrödinger equation always. Pay the price. Reality splits. The picture starts simple and becomes weird. A quantum system in superposition interacts with a measuring device. The device becomes entangled. Then the observer becomes entangled. Instead of the superposition collapsing into one outcome, the combined system evolves into a superposition of observer saw outcome A and observer saw outcome B. These branches no longer interfere in practice because of decoherence. Each branch contains a version of you with a definite memory. Each version feels unique, yet the full wave function contains them all. The weirdness here is not vague mysticism. It's a hard denial of a single outcome. Many worlds says there is no fundamental random jump, no special measurement rule, no unique history. The universe is a continuously branching structure of outcomes, all real, all equally physical. Think of a choose-your-own-adventure book. At one page, you face a decision: open the door or run away. The book doesn't erase the path you didn't pick. It still exists on other pages. You only experience one storyline because you're following one thread. Many worlds says quantum reality is like that, except the other pages aren't fiction. They're physical branches that still exist, even though your memories can only live in one. The attraction is mathematical simplicity, one rule always. No mysterious collapse postulate. Decoherence, developed in modern form through the late 20th century, explains why branches become effectively separate so you don't see interference between macroscopic outcomes. Many worlds uses that to say separation is real enough. The branches are autonomous. Another explanation is that many worlds is just a different language for the same predictions, and multiplying worlds is an extravagance. Critics point out the probability problem. If all outcomes happen, what does it mean to say one outcome is more likely? Many world supporters answer with decision theory and measure over branches, but it remains controversial in foundations. Why it doesn't fully settle it is that it gives you an ontology you can't directly count. You cannot open a door and see the other branch. Decoherence makes sure of that. Many worlds is powerful, but it is hard to empirically privilege over other interpretations that match the same data. And yet, if many worlds is true, then single version is not a feature of the universe. It's a feature of your branch. Your life is not the universe selecting one path. It's you waking up inside one thread of a much larger tapestry that never collapsed. So here's the final haunting question, the one that should stick in your throat after the screen goes dark. When you remember making a choice yesterday, are you remembering one past, or just the only past your branch allows you to remember? And that's the countdown. Click that subscribe button for more quantum stuff.